Hello and welcome back, everyone. We get to do this again. I am feeling somewhat better, so I'm optimistic this is going to be the last time. But again, I really don't want to get anyone sick, so I'm going to do whatever I'm supposed to. But anyway, I think probably Friday I'll be back, fingers crossed. But anyway, for today, we get to talk about Chapter 3, or at least start talking about Chapter 3. So again, I really can't wait to do this in person again, because it is much more fun. But hopefully this is tolerable enough. Definitely send me emails if you have any questions. Remember, the homework for Chapter 2 is due Friday, so send me questions. If you have any, I'll certainly answer the questions in class if people have any as we go about that. But anyway, Chapter 3. So Chapter 3, I've sort of written down a list of stuff that's in this chapter, and it's just a list of stuff. So this is very much a list of some stuff chapter rather than having a sort of coherent theme to it. It's basically more Chapter 2, if you want. So let's start with the definition of order. And so I'm going to warn you in advance that the word order is going to cause some amount of unpleasantness. Because order, this actually has two different definitions, depending on what thing you're talking about. Okay. One is for the order of a group, and one is for the order of an element of a group. And there's some kind of weird backwards justification for why we'd use the same word for two different things that we'll come across later that will maybe sort of justify this. And once you've fully immersed yourself in this and acclimated to it, it won't be something that causes you confusion. But while you're first learning it, this will definitely be something that will cause you some amount of confusion based on my experience. So I want to be very clear. There's two completely different senses of this word. I'm going to go over both of them today, and I'll just try and warn you that, yes, they're different. So first of all, let's start with the simple one, which is the order of a group. So the order of a group is just the number of elements in the set. Or I'll just write the number of elements in the group. And we denote this just by putting these sort of like absolute value bars around G. So this is just the number of elements in G. So just as some examples, most of our original friends that we started at the very beginning, Z, R, Q cross, etc., these things are all infinite. So if you want, you could just write that these things all have order infinity. That's because these sets have infinitely many elements. Now, if you really want to nitpick, you could argue that this has a different size of infinity than this. We're not going to fuss about that in this course. We're really, in this course, only looking to distinguish between groups that have an infinite number of elements and groups that don't, groups that have a finite number of elements. So we'll sort of be splitting things into finite and infinite. So all, again, that we mean when we say a group is finite is that the order of the group is finite. So that is an important distinction for us. Okay. And again, order is the number of elements. So finite just means it has a finite number. So it has, for example, 6 elements, or 8 elements, or 12 elements. So some examples of finite groups include Z12, which has 12 elements. Remember, it has the elements 0, 1, 2, up to 11. The remainders after dividing by 12, if you like. Z12 cross, remember, this is the things that are relatively prime to 12. So that is 1, 5, 7, and 11. So this actually has order 4. So again, this is just the number of elements in Z12 is 12. The number of elements in Z12 cross is 4. The number of elements in, say, the Klein 4 group, it's also 4. The number of elements in Q8, the quaternion group, as we've called it, that is 8. The number of elements in D8 is 8. Although, as was pointed out by someone in the last video, I couldn't keep straight whether I was calling it D4 or D8, because I said I was going to call it D8, and then I accidentally called it D4 at least twice during the video. By D8, I mean the symmetries of a square, so there are 8 total elements in that. Anyway, so these are some of the finite groups that we've talked about. I guess a really silly example we could talk about is we've talked about this group 1 and -1 that has order 2. The trivial group, I guess, has order 1. So this is a variety of examples of finite groups. In fact, this might be all of the finite groups that we have listed so far, or very close to. Now, what about the order of an element? That's the other thing we want to talk about. And so to talk about the order of an element of a group, what we want to do here, we want to fix a group G. So imagine that we have G here. This is some group. Okay, and I'm not specifying what group it is, which means I'm going to write the operation of this group as though the operation is multiplication. But remember, it could be anything. And I'm going to pick some X, an element of G. Now, I'm going to look at a list of elements. So I'm going to start with X, and then I'm going to look at X squared, X cubed, X to the 4th, X to the 5th, and so on. And I'm going to look at this list. Okay, and remember, I'm writing this group multiplicatively, so this is just X, X star X, X star X star X, X star X star X star X star X, etc. Down this line. And so these are just a bunch of times of ways of combining X with itself. Okay. And the key observation here that's going to sort of inform a lot of what we're talking about is that if G, the group itself, is finite, this list has repeats. Now, this is a really specific application of what's generally called the pigeonhole principle. So the pigeonhole principle is this general idea that if you put 10 things in 8 buckets, then there has to be a bucket with more than one thing in it, because there's more things than there are buckets. In this case, this is an infinite list, and if the group is finite, then what we're really saying here is if you put infinitely many things into finitely many buckets, then there's a bucket with more than one thing in it. That's all I'm really saying here when I say that this list has repeats. So this is, in some sense, the silliest statement of the pigeonhole principle possible. But this turns out, this observation, although it's not a difficult observation to make, it turns out to be a really important and useful observation to understanding what's happening. Because what does it mean when I say that this list has repeats? Well, it means that there's 2 powers of X that are different powers of X, but are actually the same. So this means that there is I and J in the positive integers, such that I is not equal to J. So all I'm doing is I'm saying, like, say that one and that one are the same or whatever. I'm just naming the 2 exponents that happen to be the same, such that X to the I is equal to X to the J. And now we'll do the mathiest thing ever and just say, without loss of generality, let's just say J is bigger than I. All I'm saying here in a excessively pedantic way is that one of I and J, since they're different, one of them is the bigger one. Let's just say it's J. And then all I'm going to do is I'm going to multiply this equality by X inverse I times. Okay, so by X inverse to the I-th power. Now remember, this is a group, so I know there is an inverse, so I know I'm allowed to do this. And so what does this leave us with? Well, on the left-hand side, if I multiply X to the I by X to the inverse to the I, then these things are going to, and last time I said xylophone away, but it was pointed out, in fact, I meant accordion away, because an x and an x inverse are going to cancel, and then another x and an x inverse are going to cancel, and then another x and an x inverse are going to cancel, until what I'm left with on the left is going to be E, just the identity element. Nothing else is going to survive. And that's going to be equal to x to the j minus I. And the only thing here I really want to notice is that j minus I is positive. And so in particular, what have I proved here? I've proven the following, I think, very non-obvious proposition, which is that if G is a finite group, and X is some element of G, then always there's some positive integer K such that X to the K is the identity. Right. So in other words, if you start with a finite group, pick any element in the finite group that you want, and then raise that element to power after power after power after power, you're always eventually going to make it back to the identity. That's what we've proven here. Okay. Now, I really want to emphasize here, this is entirely contingent upon the fact we started with a finite group. If you choose an infinite group, this may well not be true. For example, if you take the element 2 living inside the group R cross, 2, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, keep going as long as you want, you're never going to get back to 1, which is the identity of R cross, right? That will never happen. But if I take something like 2 inside some finite group, like let's say Z15 cross, then 2 squared is 4, 2 cubed is 8, 2 to the 4th, hey, that's actually 1. We did get back to 1. So what we're saying here is in every finite group, start with any element you want and look at its powers, and you're always going to get back eventually to the identity. And this is ultimately a consequence of this weird, almost trivial pigeonhole principle observation that I can't write down a list of infinitely many distinct things inside a finite set, and so I'm going to have repeats, and then throw around some group axioms, and magically that turns into this statement, which is, again, I think very non-obvious, that if your group is finite and you start with an element, then one of its powers is eventually going to be the identity. Now, roughly speaking, when I go to define the order of an element of a group, I'm going to say it's the power that's the identity. But there's a slight problem with that, which is that if I take, for example, again, 2 in Z15 cross, 2 to the 4th is the identity, but 2 to the 8th is also going to be the identity. 2 to the 12th is also going to be the identity. So I can't really specify the power that's the identity. What I have to actually define is the smallest power that's the identity. So let me go ahead and write that down officially, but that's what the order of an element of a group is going to be. So G is a group, X is an element of G. The order of X, the smallest positive integer K, such that X to the K is the identity. Yeah. If G isn't finite, this might not exist, in which case then we just say the order is infinite. But again, just to reiterate how we've been saying this, our proposition before here that if G is a finite group, then there's and X is an element of G, then there exists a positive integer K, such that X to the K is the identity. This exactly guarantees that the order exists. So that proposition that we said before, I could rephrase to just say the order of every element of a finite group is finite. Okay, so some examples. Well, we've done 2 and Z15 cross. So the way we write this, and our notation is exactly the same. We just put an absolute value bar here around 2. This is 4. Okay. And that's because the smallest power of 2 that's equal to the identity is the 4th power, the smallest positive power. The 0th power of everything is the identity by definition, but we're not going to count that because that would be a not very interesting definition. What's the order of 4 in this group? Well, 4 is not the identity, but 4 squared is the identity, right? Because 4 squared is 16, which is 1 mod 15, so the order of 4 would be 2. What's the order of 1 going to be? Well, 1 to the first is already the identity, so that's 1. Okay. Let's look at Q8. Okay. So let's take, say, I in Q8. What's the order of I? Well, that's saying I should look at the list of I to the first is I squared is -1, I cubed is -I to the fourth is 1. The order here is that 4. Okay. Now, you might, in some sense, you might think of this as being the period, because if I actually kept going, if I just didn't notice that I'd gotten to 1, and I just kept going, and I wrote this down forever, this is actually going to repeat in this loop, I -1 minus I1, I -1 minus I1, etc., etc., etc. It's going to repeat in that loop forever. And that loop has period 4. And so I think there's a good argument that instead of calling this the order of I, they should have called this the period of I. But no one asked me, so instead we get to call it the order of I. And we go with that. So the order of I is in fact 4. What about, let's say, A inside the Klein 4 group? What's the order of A? Well, we write down A squared. Well, A squared in the Klein 4 group, that's the identity, remember? So the order of A is 2. Great. Let's just in general answer, if I have any group, and I take E inside that group, the identity, what is the order of that? Well, E to the first is E, so the order of the identity is always 1. In fact, you can convince yourself, if you are into this sort of thing, that that's actually an if and only if statement. An element has order 1 if and only if that element is actually the identity. Because if you say something has order 1, you're saying it to the first power is the identity, which says that it is the identity. And on the other hand, if the element is the identity, then it to the first power is the identity, so it has order 1. So the only things of order 1 are the identity. Okay. Now, just to be clear, nothing stops elements of infinite groups from having finite order. Elements of infinite groups can have finite order. So, for example, -1 is an element of the group R cross. And so, as an element of the group R cross, what's the order of -1? Well, -1 squared is 1. And so the order of -1 is 2. Okay, talk about upsetting looking statements to write down. Absolute value of -1 is 2. But again, this does not mean absolute value for us. This means the order. And so what this is communicating is that -1 squared is 1, the identity. Okay. In fact, actually, exactly what we did here with Q8 and I would actually work just exactly the same if we took I inside the multiplicative group C cross. There, it would still be true, even though C cross is an infinite group, the order of I is in fact 4. Okay. But if I took something like the order of 3 inside this group, and I'd be writing down 3, 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th, and so on, and that would go on in this loop forever. Or sorry, that would go on forever without ever sort of looping. This is going to end up being an element of infinite order. And so again, just to summarize, the thing to keep in mind here is if you're in an infinite group, the order of your elements might or might not be finite. But if you're in a finite group, every element will have finite order. Okay. Let's look next at the order of 4 in Z10. Okay. And so here is one of our first opportunities to be tripped up by the fact that, remember, the operation of Z10 is addition. Right. And so don't let that trick you, because you might sort of start saying, oh, well, I know what 4 times 4 is. 4 times 4 is 6 times 4 is or whatever. But multiplication's not the operation in Z10. The operation in Z10 that makes it into a group is addition mod 10. And so that means when I write out this list, I don't write out 4 to the first. I wrote out 4, and then 4 plus 4, and 4 plus 4 plus 4, and 4 plus 4 plus 4 plus 4. And so that is 4, 8. That's 2. That's 6. 4 plus 4 plus 4 plus 4 plus 4. That is 0. Okay. So this is, so to speak, 4 to the 5th. Okay, but you would never want to call this 4 to the 5th because it would break, it would probably break your brain. It would certainly break mine. Because, I mean, this is 4 combined with itself 5 times, but we don't want to call it 4 to the 5th. We will just go ahead and immediately, though, say the order of 4 is 5 in this group, because I do have to combine it with itself 5 times. But I probably want a better way to write this. And the way I will write this is 5 times 4. Okay. And now this is super weird because of what's happening here. Because actually this 5, this is living in Z plus, and this 4 is living in Z10. And so if you're paying close attention to what we're doing, this seems like the kind of thing that we're explicitly not doing. But this isn't actually any different than when we wrote down 2 to the 4th, and this 4 here in the exponent, that was living in Z plus. It just so happens that multiplication, when we go back to how we think about what multiplication means, if you go back to sort of like the second grade definition of multiplication, multiplication means repeated addition. And so when I say I want to add 4 to itself 5 times, the way that I express that is multiply 4 by 5. Okay. But note that means that this times here is not really a binary operation. I mean, it's not in any sense a binary operation or anything like that. That's fine. This is just a shorthand way of saying add this thing to itself a bunch of times. Okay. So what's the order of 1 in Z12? Okay, again, this is a group under addition. So when I go to ask the order of 1, I'm asking how many times do I have to add 1 to itself in order to get the identity of Z12, which is 0. And the answer is I have to add it to itself 12 times, because I have to go to 1 plus 1 plus 1 plus dot 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 plus 1 12 times. So the order of 1 is, in fact, 12. Okay, what's the order of 3 in Z12? Well, that's only going to be 4, because if I add 3 to itself 4 times, I get 3 plus 3 plus 3 plus 3, that's 0. Great. What's the order of 9? Okay. Well, that's also going to be 4. Because if I add 9 to itself once, then I get 6, I add 9 to itself 3 times, I get 3, and then I add 9 to itself 4 times, and then I do indeed get 0 again. So just be very mindful when calculating the order of elements in groups. Remember to use the operation in the group, not just multiplication because we wrote the definition with multiplication, because we're going to write all of our definitions with multiplication. So, reminder, just to summarize, if I take the order of a group, this is just number of elements. It's nothing more than that. If I take the order of an element of a group, this is the smallest positive power equal to the identity. So these are our two different senses of the word order, and just be aware we're going to use both of these quite extensively through the rest of the course. So just be aware which one is being referred to. We'll sort of switch back and forth depending on exactly what we're talking about. The next thing I want to talk about is the idea of a subgroup. And so probably by this point in your math career, almost you could write down the definition of a subgroup just by reading the fact that it's the word sub in front of the word group. What is it? It's a subset of a group that's also a group. And so the one key thing that you want to keep in mind, and the one key point here, is it has to have the same operation. So a subset H of G, a subgroup of G, if it is a group with the same operation as G. All right. So, for example, and our notation here is going to be to use a weird less than equal sign. So Z is a subgroup of R because the reals are a group, remember, under addition. Z is a group under addition. It's the same addition, all of that kind of thing. It's all good. Another example that we'll like to go to, 2Z is a subgroup of Z. Now, I don't think I've written down 2Z before. What is 2Z? This is our even numbers. So the even integers, those are also a group under addition, and those are a subgroup of the integers themselves. There's another group I don't think we've written down before. R plus. So that's the positive real numbers. To think for a second, what operation are the positive real numbers a group under? Well, this turns out not to be too difficult of a question, because you're basically choosing between addition and multiplication. But the positive real numbers don't have 0 in them. So they can't be a group under addition, right? Because they don't have the identity of addition. So if they're a group under anything, it must be multiplication. So you've got to check for yourself real quick. Are the positive real numbers a group under multiplication? And the answer is yes. If I multiply 2 of them, I get a positive real number. The identity 1 is in there. And every positive real number has an inverse, which is also a positive real number. So in fact, we get this complete nonsense-looking statement that R plus is a subgroup of R cross that is just notation soup, because here this cross is sort of trying to communicate the group of the reals under multiplication, because I threw out 0, you'll remember, to get the reals to be a group under multiplication. And now this plus is denoting positive, and so this plus has nothing to do with the binary operation, but this times is trying to indicate the binary operation. Try not to get too wrapped up in the notation here. The positive reals are a subgroup of the multiplicative group of non-zero real numbers. That's all that's really being said here. Okay. Now, important to note, being a subgroup is a lot more than being a subset, because of this requirement about having the same operation. So R cross is a subset of R. It is not a subgroup of R. Okay, even though every element of R cross is also an element of R, it's not a subgroup because the operations are different. Okay. There's one sneaky one in here that I just want to point out because it's very easy to fall for. Z12 is not a subgroup of Z. Okay. Z12 is a subset of Z. 0 through 11, all those are in Z. And you might say, the operation here is addition and the operation here is addition. But remember, it's a different addition. And what does it literally mean when I say it's a different addition? It's a different addition because when I add 11 and 11 here, I get 10. Whereas when I add 11 and 11 here, I get 22. And 10 and 22 are different numbers. And so they're not the same operation. And so even though we use the same symbol to denote the operation here and the operation here, which again, you might complain I shouldn't do, but we do, the operations themselves are actually different. So Z12 is not a subgroup of Z. Again, different operations, but more subtly. Now, there are two sort of silly versions of subgroups that you always get. So for any group G, it's always the case that the identity is a subgroup, because this is a trivial group. This is called the trivial subgroup. And it's also always the case that G is a subgroup of itself, albeit I'd actually argue this is even less interesting than that one, but neither of these is very interesting. This is called the improper subgroup. Okay. And so the phrase that you'll see on the homework and in theorems and all these sorts of things is you'll see all the time the phrase non-trivial proper subgroup. It just means any subgroup of a group that's not one of these two. So any subgroup that is neither the trivial one nor the improper one. Just to show you, here's an example of a subgroup of Z12. So this is the sort of, so to speak, even elements in Z12. 0, 2, 4, 6, 8, 10. These things are, in fact, a subgroup of Z10. You can check that if you add two of them together, you always get back something in this set. And you can also check that everything's inverse is also in here. So 0 inverse is in here, 2 inverse is 10, 4 inverse is 8, 6 inverse is 6. So this thing stays a subgroup. Okay. Don't try to generalize this too much, though, because if I try and take, say, 0, 2, 4, 6, this thing is not a subgroup of Z7. And so you might think, I just did the same thing, but it didn't quite work. And the reason why it doesn't work is 2 plus 6 is 1, which isn't even in this set. And so this thing here is not even closed under the operation. And so you might figure out something went very wrong when I tried to translate this example to here. And you can try and figure out exactly what it is that went wrong. Okay, so let's prove something that you might be worried about, but that you don't actually need to worry about, which is that if H is a subgroup of G, then the identity of H is the same as the identity of G. Right. So what do I mean by this? Because this is also sort of notational soup. H, if it's a subgroup of G, remember H, that means is a group. G is a group. Every group has an identity. We'll call the identity of G, EG. We'll call the identity of H, EH. My claim is that those are actually the same. regardless of what subgroup we choose. We can't sort of change the identity. Okay. And the proof here is a very, very funny proof, actually. So, namely, what is the proof? The proof is to consider what happens if I multiply EH by EG. And so, what is it that I get? Well, these things are both in. These things are both in G. And so, therefore, if I multiply anything in G by the identity of G, I get that thing. So, since EG is the identity of G, we have EH times EG. That thing is equal to, and so that's going to be EH. But now, I claim that's also equal to EH times EH. Because EH is in H, and so anything in H that I multiply by the identity of H, I'm going to get the identity, or I'm going to get that thing back. So in particular, if I multiply the identity of H by the identity of H, I should get the identity of H. But now, what have I done here? I now have this equation EH times EG equals EH times EH. But now I'm primed to do left cancellation, because remember, the last property we proved at the end of the last chapter was that we can cancel something off of the left. So if you want to be really pedantic about it, what are we going to do? We're going to multiply both sides of this equation by the inverse of EH in G on the left. But because we've already proved groups are left cancellative, we don't have to reprove that. So instead of thinking about that really confusing string of words I just said, we can actually just say by the left cancellative property, we can do that. So EG is EH by left cancellation. Okay. So that's our proof here. And so what is it you should take away from this? You should take away from this that every subgroup of a group starts with the identity. You can add in some other stuff, but whatever other stuff, you always have to contain the identity. So if you have any subset of a group that doesn't have the identity, it can't possibly be a subgroup. It always has the identity in it, living in it as the identity of the subgroup. So basically, that means you don't have to worry about this whole subscript nonsense anymore, because you know that the identity of the big group's also the identity of the small group. And so you only really need to keep track of one E when you're keeping track of one of these chains of subgroups. One last thing for today, and this is going to be ultimately the connection to this idea of order. And that's that there's one specific subgroup that we can always write down for each element. And so here is a sort of general theorem. So if X is an element of a group G, then this set, I'm going to denote like that. So I'm going to define it here to be, and this colon equals just means define to be. So this thing is going to be every power of X. This thing is always a subgroup of G. It's a collection of all the powers. Okay. This thing is called the subgroup of G generated by X, if you are looking to name it out loud. Okay. Now, what do I have to check to verify that this set is really a subgroup? Remember, we have to check our group axiom. So it has to be a binary operation. It means it has to be closed under the operation. Well, if I multiply two things in this set, what am I going to get? Well, I'm going to get x to the I times x to the j, because everything in this is just a power of x. That's x to the I plus j. It's definitely in there. It's closed. It needs to have an identity. Well, E's in there by definition. It's got our identity. It needs to be associative. But the nice thing is G is already a group by assumption. So any subset of G is going to be associative. So associativity actually is free. And then the last thing we need is inverses. I realize my formatting here has gotten completely off. But anyway, I'll just write it over here. Well, of course, x to the minus third is the inverse of x cubed. And so inverses are also in there. And so this thing is almost a subgroup just by definition. You don't have to do that much to show that it's a subgroup. But this gives me access to a whole wide world of subgroups in any particular group that I want. So let me just do some examples of this just to show you what it is that's happening here. So let's again go back to our friend Z15 cross. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So here are the 8 elements that live in Z15 cross. Remember, it's the ones that have no common prime factors with 15, so the numbers that are not divisible by 3 or 5. And if I take the subgroup generated by something, all I'm doing is I'm taking the powers of that element. So in this case, if I take the subgroup generated by 2, I'm going to get 2 squared, which is 4, 2 cubed, which is 8, 2 to the 4th, which is 1, and then the remaining powers. But the remaining powers are actually just going to wrap back through this same set. So here you'll notice I included both the positive and the negative powers in my definition, but here actually the positive powers of 2 and the negative powers of 2 ended up being the same, and that's because this group is finite, and so we end up with this repetition that we talked about earlier. So in this case, the subgroup generated by 2 is just this. And again, just in case you don't believe me, what is 2 inverse? 2 inverse is 8, 2 to the minus 2, it's 4, and so on. All the negative powers are just wrapped up in this same set. So the subgroup generated by 2 is just these 4 elements. Okay. What about the subgroup generated by 14? Well, the subgroup generated by 14 is going to have 14 in it. Note, the subgroup generated by x is always going to have x in it. But then it is going to have x squared in it, and so you have to do a little bit. You might see I tried to do the 7 and then decided that my brain wasn't up for computing powers of 7. But I'll let you compute 14 squared, and 14 squared mod 15 is 1. And so, in fact, actually, the subgroup generated by 14 in this group is just 1 and 14. What if I take Z15 instead? So notice I've now switched from Z15 cross to Z15. So now the operation's addition. Now what if I take the subgroup generated by 3? What's that going to be? It's going to be 3. And now remember, the next thing is 3 plus 3, because I'm now talking about addition. So it's 6, 9, 12, and 0. And then I'm going to repeat through this same list again and again and again. And so I'm going to end up with all the multiples of 3. If I took the subgroup generated by 6 instead, what would I get? I would get 6 and 12 and 3 and 9 and 0. So notably, these two things are the same. So pay close attention to that. That can happen. But I end up getting the same set, but that is my subgroup. The only time you need to worry about this sort of negative powers of x piece of the definition is when the group you're working in is actually itself infinite. And so, for example, if I take 2 living as an element of the positive reals, and I look at the subgroup generated by 2 here, that I really am going to need not just 2, 4, 8, 16, 32, etc., etc. If I only take the positive powers of 2, it's not going to be a group because I don't have the identity and I don't have inverses. So I'm going to need to also add in the identity, which is 1, and then also add in the inverses of all of these. So 2 inverse, 4 inverse, 8 inverse, 16 inverse, etc. Okay, and so that is just exactly the elements here. Now, I'm cramming this here at the end of this video because I want to rationalize for you why it is that people use the word order for the 2 things that we've used order for. And so here is the rationalization. And that's that if you look at the way this all works out, the order of the element x, it's actually the same as the order of the subgroup generated by x. Okay. And so remember, the order of a group is the number of elements in the set. The order of an element is the smallest power that gets you the identity. It turns out these 2 things are always the same. And if you in fact look back at this whole bit, what did we do when we found the subgroup generated by 2? The subgroup generated by 2 in Z15 cross, we found by writing down 2, 2 squared, 2 cubed, 2 to the 4th until we got back to 1. Well, that's exactly how we found the order of 2. We figured out, okay, well, I multiply 2 by itself. 2, 2 squared, 2 cubed, 2 to the 4th is the identity, and that's where I stop. Okay, so these 2 things are actually connected in that the order of an element is the order of a subgroup associated to the element, which is then just the same sort of sense of order. It leads to confusion. I wish it were a little bit different, but alas, it is what it is. All right. So I'm going to wrap up here for today. I will, again, hopefully be back on Friday, and my intention is to do a bunch more examples of this order of an element, subgroup generated by type of thing, and also answer any questions you have about the homework. Hopefully, fingers crossed. All right. I hope you are happy and healthy. I hope life is going well. Email me if you have any questions, and I hope to see you all real soon. Have a great day. Bye for now.